limits when x goes to either infinity or negative infinity. So the first box up here has some examples from previous courses where we're just asked to give the horizontal asymptote. So when you do this, you want to look at the degree of the numerator and degree of the denominator. Degree is the largest exponent. So in the first one, the degree of the numerator is 1. That's the largest exponent. And the degree of the denominator is 2. If it's bigger on the bottom, the horizontal asymptote is y equals 0. Hopefully that's something you memorized in a previous course. On this one, if you were to multiply out the top by foiling, you'd have 3x squared and then some other terms. I don't care about the other terms because when I go off of the graph, way off to the right to see what's happening with the horizontal asymptote, I care about what's happening going toward infinity. And if I have something to the x squared power, the other terms aren't going to be as significant as the term that's squared. So I'm going to ignore those other terms, and likewise in the bottom, I'm ignoring the other terms that don't have the largest power. If you have an equal degree in the numerator and denominator, degree 2 and degree 2, your horizontal asymptote is the ratio of the leading coefficients. So in this case, the horizontal asymptote is y equals 3 over 1, or just y equals 3. Next, the degree of the numerator is greater than the degree of the denominator. What's going to happen on this graph is going toward infinity, the graph is going to get huge. The top is going to get much bigger faster than the bottom, and so our graph does not flatten out and become horizontal. It's going to shoot up toward infinity. So we say this one has none, no horizontal asymptote. Okay, number 4, if you FOIL it out, you can see on the bottom you're going to have a degree 2. And the top, you can see that the biggest power is 1. If it's bigger on the bottom, y equals 0. Hopefully you can see on this next one that you'd have a degree 3 in the numerator if you multiplied x times x times x. In the denominator, you have degree 1. If it's bigger on the top, there's no horizontal asymptote. It does not flatten out toward infinity. And number 6, we have degree 6 and degree 6. We look at the ratio of the leading coefficients if we have the same degree. Make sure you're looking at the coefficients in front of the x with the largest powers. And so this horizontal asymptote is y equals 2/7. When you write a horizontal asymptote, you need the y equals because it's the equation of a horizontal line. Now let's switch gears from pre-cal to calculus. Now when we're doing calculus, we're going to find the limit as x approaches infinity. And basically that's the same as the horizontal asymptote, because if I look at a horizontal asymptote of y equals 0, that's what's happening as we move off the graph toward an x value of infinity. So on this first one, if you look at the larger degree on the bottom, that means the horizontal asymptote is y equals 0, so our limit is going to equal 0. If the degree of the numerator is less than the degree of the denominator, we have a limit of 0. Or you can remember, if it's bigger on the bottom, it's 0. Bobo. Okay, next one is BOTI. If it's bigger on the top, it's infinity. So this one's bigger on the top, so our limit would be infinity. So instead of saying no horizontal asymptotes, we're going to say that the limit of the graph is going to approach infinity. The top is going to get bigger much faster than the bottom, so the graph goes toward infinity. Now, Betsy, if the bottom equals the top, we look at the coefficients. If the bottom power equals the top power, we look at the coefficients, and our limit is 3/5. Okay, so one other little thing you have to be cautious of is you have to check the sign whenever the degree of the numerator is larger than the degree of the denominator. For example, on this one, we have degree 3 over degree 2. So we have to check the sign. We know it's going to get bigger on the top, so our answer is either going to be infinity or negative infinity. Let's imagine plugging, since we're going to infinity, let's imagine plugging a big number in the top here for x, like a trillion. If I cube a trillion times 2, does the 5 even matter? No, the 5 is going to be insignificant compared to how big that other number is. But the sign of that number is going to be negative because I'm cubing a big number and then multiplying times a negative. So I'm going to get a negative. On the bottom, I'm only really considering plugging into the x squared because when I square a huge number, the 4 to the x is going to be insignificant. But squaring a big number gives me a positive. A negative divided by positive is going to give me an answer of negative infinity. Okay, next one. Bigger on top, so it's going to be infinity. BOTI, bigger on top, infinity, but we have to check the sign. Again, think about plugging a big number in here. Now remember PEMDAS. You're going to do your exponent first, then multiply by that negative sign. So when you do the exponent first, it stays positive. When you multiply by a negative, you get a negative. Same thing on the bottom. The 6 is insignificant when we plug in a huge number. Let's square a big number, stays positive. Multiply it by a negative, it becomes negative. So if we have negative divided by negative, our answer is positive infinity. Okay, last one here. It's bigger on top, BOTI, bigger on top, infinity. Let's check the sign. When I plug in a number to the top, a big number, I get positive. Plug in a big number to the bottom, I also get positive because that minus 11 is insignificant. Positive divided by positive gives me positive infinity. Okay, pause the video and try the next 3. Okay, the first one, bigger on the bottom. Bobo is our little mnemonic device, and that one equals 0. The next one, BOTI, bigger on the top, it's infinity, and we're going to positive divide by negative, so we get negative infinity. And the last one's Betsy. Bottom equals top, we look at the coefficients. And so the ratio of our leading coefficients is negative 2/7. Okay, so we're going to now look and see which of these functions do you think grows fastest as x gets bigger. So we have an exponential, a log, a square root, x cubed, x to the 20th. So I want you to rank these from what you think grows slowest as we plug in bigger and bigger x's to which one grows fastest. So list them in order from slowest growth to fastest growth. And then we'll fill out this table. So pause the video and rank them. Okay, so let's say you wrote down a guess like this. At this point, what we would do in class is we'd get out our graphing calculator and fill out this table by using the y equals and the table of our graphing calculator. But I'm going to pause the video, fill it out for you, and then we'll check and see if we guessed the correct order for ranking our functions from slowest growing to fastest growing. So give me a minute to fill out the table, and I will be back. Okay, so these numbers in the table aren't super important, but they're just going to help us see like a pattern or kind of get some evidence about which of these functions grows the most quickly. Well, obviously, log grows very, very slowly. Even if I plug in 1,000,000, my output is only 6. So that's the slowest growing function. The next one is square root x. That one does not grow very quickly, even as x gets very large. Looks like the next one is x cubed. What error means, it means that the number is too large. It's just exhausted the capability of the calculator. The calculator doesn't have enough ability to work with that many decimal places or that many places in a number. So it's not really an error, it's just beyond the capability of the calculator. But the next one would be 10 to the 20th power, and then finally 10 to the x. So an exponential function is going to grow bigger faster than x to a power. Even if we had like x to the 1,000,000 power, 10 to the x is going to grow faster when x goes toward infinity. Eventually, this power is going to get much, much bigger than a million. And so eventually, as we go toward infinity, the exponential function is going to grow faster. So how does this apply to limits? Well, same thing we've been doing. We just want to see where the function is bigger, on the top or bottom. So this one is bigger on the bottom, Bobo, so we get 0. Let's look at the one to the right. Exponential is the fastest growing than anything, so it's bigger on the bottom. Again, 0. For the same reason, this one's bigger on the bottom. And the one on the lower right-hand corner, exponential on the bottom. This is just a polynomial. It's like x to any power, like x to the 5,000, x to the 3. We don't know what that power is. It's just an integer. So it's bigger on the bottom because of this exponential function. And so that one's going to be 0. Okay, let's talk about this one on the right. So it's bigger on top because the log is the slowest growing function. So if it's bigger on top, it's infinity. So why don't you pause the video and try these other 5. Okay, hopefully your answers match mine. You're looking to see which function grows the fastest and finding the limits accordingly. Okay, so for finding limits to negative infinity, looks like my picture got a little bit cut off the screen, but I think you still read it. When the degree is larger on top, you have to check the sign. Okay, this first one, it's not larger on top, so all we have to do is look at the ratio of the leading coefficients, -1/2. Even over here on B, when we go to negative infinity, if it's the leading coefficients, if the degree is the same, you still just have to look at the ratio of the leading coefficients. You do not have to check the sign. You can, but you'll find out that you get a -1/2. Because if I were to plug in a negative here and square it, that would give you positive times a negative makes it negative. Plug in a negative here and square it, times 2, that would be positive. So negative divided by positive does give us a sign that's negative. Okay, C, that one is bigger on top, so we have to check the signs. So it's either going to be infinity or negative infinity if it's bigger on top. So if we plug in a positive number for x up here, we get positive. Plug in a positive number for x here, we get positive. Positive over positive is positive infinity. Look at the one to the right. Same problem, but now we're finding the limit as x approaches negative infinity. You've got to check the sign. Plug in a negative number here. When you cube a negative, it's still negative. However, in the denominator, when you square a negative and then multiply by 2, you get a positive. So negative divided by positive is negative infinity. On E, bigger on the bottom, our limit 0. F, we're going to negative infinity. It's 0 on the, or it's bigger on the bottom, so the answer is still 0. If you got -0, that would still be 0. So you don't need to check the sign. G, we're going to, as a limit as x approaches infinity, it's bigger on top, so we have to check the sign. We plug in a positive for both. They would stay positive. Positive to the 7th power and positive to the 5th power times 2. Positive divided by positive is positive infinity. Let's plug in here. A negative to the 7th power is going to remain negative. A negative number to the 5th power is negative, times 2 is still negative. Negative divided by negative is positive infinity. Okay, example I. This one's like a tricky one. What I'm going to do is I'm going to think about plugging in. And when I plug in, I'm going to get like a negative e to the negative infinity and then negative infinity squared. I can't really plug in infinity because it's not a number, but this is kind of giving me an idea what's happening. Well, that looks like two things that I don't really know how to multiply. So let's go ahead and think about a number approaching infinity, like negative 1 million. I'm sorry, a number approaching negative infinity, since that's what our limit is. And then let's plug in negative 1 million here. Is negative 1 million anywhere close to negative infinity? No way. But it's heading in the right direction. So it kind of gives us something to think about. Ooh, we have a negative exponent. We can move that term with a negative exponent to the bottom. Just like if you had a problem with like an x to the negative 2, you could move that to the bottom and make it 1 over x squared. In the same way, we can move that e to the negative 1 million to the bottom and get negative 1 million, oops, I forgot the squared because there's a squared in the problem. I can get negative 1 million squared over e to the million power. Now when I've written that expression as a ratio or a fraction, now I can see which function grows faster and figure out the limit. So on this one, the bottom gets bigger faster, so that means our limit is going to be 0. Almost done, just a couple more to do. Okay. This question, A and B, is pretty tricky because it just says give the horizontal asymptotes. But these are exponential functions. 3 to the x are exponential. When we first started out our notes and we gave horizontal asymptotes right here, oops, that's not the highlighter. When we gave horizontal asymptotes right here, these were not exponential functions, they were just polynomials. So it works different now that we're no longer looking at polynomials, but we're looking at exponential functions. So when we find the horizontal asymptotes, we have to consider two different limits. What happens when x goes to positive infinity, and then what happens as x goes to negative infinity. So let's determine our limit as x approaches positive infinity first. Well, when we go to positive infinity, that 3 to the x is going to get huge. So in comparison, the 4 and the 5 are insignificant. Am I allowed to cancel them out with algebra? No. But I can disregard them with finding the limit. So kind of what I have in top here is I have 4 minus 1 times 3 to the x. And on the bottom, I have 5 plus 2 times 3 to the x. I just wanted to show you that minus 1 there because that's like my leading coefficients. So since the 3 to the x's grow at about the same rate, I'm going to look here at my ratio of my leading coefficients to get my limit. Okay, let's consider what happens as x approaches negative infinity. So as x approaches negative infinity, let's look at our graph of 3 to the x. So 3 to the x, as we go off to the left, it's going to approach an output of, it's going to approach an output of 0. Our y value is going to approach 0. So now, going to negative infinity, these circled terms are insignificant. They're going to get so tiny, such a small decimal, I can ignore them. And so going to negative infinity, my limit's going to be 4/5. So to answer the question they gave us, the horizontal asymptotes are y equals negative 1/2 and y equals 4/5. Okay, B, same idea. If we're finding the limit of this expression as x approaches infinity, the 8 to the x is going to dominate the value. The little constants 1 and 2 are basically insignificant. I'm going to put a 1 times 8 to the x so I can kind of see the leading coefficients better. So finding our limit as x approaches infinity, we want to look at the ratio of the leading coefficients or the coefficients on those exponential terms. So I'm going to have like 1, there's like an invisible 1 here. 1 divided by negative 1 is negative 1. Let's find our limit as x approaches negative infinity. So again, approaching negative infinity, these exponentials are going to go towards 0. So these guys are now basically insignificant. They're so tiny, we can just disregard them. So the limit as x approaches negative infinity is just negative 1/2. Now that 1 and the 2 that were so little when we headed off to infinity, those are now determining our limit. Since now the 8 to the x is getting smaller and smaller and smaller, closer to 0. So to answer the question, what are the two horizontal asymptotes of this graph? Y equals -1 and y equals -1/2. Okay, let's look at C. So we have limit as x approaches infinity of sine x. Well, the graph of sine x looks like this. So as our graph goes toward infinity, is this going to narrow in or approach any one specific y value? No. It's going to oscillate between many y values as it goes to infinity. So this one is DNE, does not approach any one y value. However, the next one, as x goes to infinity, the denominator is going to get huge. The biggest the numerator ever gets is 1. But we're going to be dividing by a bigger and bigger number. So as our graph goes off toward infinity, the period of the graph is going to stay the same, but the amplitude is going to get smaller and smaller and smaller. Our graph is going to approach 0 because I'm dividing by a bigger and bigger number on bottom. So that one's 0. Okay, example E. This is our limit laws. And if we have two limits that exist and we want the limit of the sum of those functions, I can find the limits separately and then sum them up. And both of these limits exist. The limit as x approaches infinity of 32, well, if I look at the graph of y equals 32, no matter where I go on that graph, the limit is always 32. Even heading toward infinity, the limit's still going to be 32. Now let's find the limit of this expression. Limit as x approaches infinity of x over x squared plus 3. It's bigger on bottom, so that limit is 0. So adding, we get 32 as our overall limit. Okay, F. What a lot of students want to do with a problem like this is square root both terms. That's not correct algebra. You cannot square root both terms if you have a plus or a minus sign here. You could only do it if you had like two terms that were multiplied together, like 9 times x squared. You can simplify that as 3x. But this first thing I showed you, you cannot simplify that. But the square root is going to somewhat reduce that squared, even if I'm not allowed to do this algebra and actually square root the radicand. I can consider that denominator as degree 1. I can't algebraically write it like this, but I can consider it to only grow as fast as a degree 1 polynomial. The numerator is also a degree 1 polynomial. So if I have a ratio of if I have the same degree, I'm looking at the ratio of the leading coefficients. So the ratio of the leading coefficients is 7 over root 9, or 7/3. Okay, I told you previously you only need to check the sign if the power is bigger on top. I'm going to put an asterisk here because this is an exception. So on this problem, and these kind of problems, you have to check the sign. So this is the same thing. It still is going to act like a degree 1 over degree 1. So our limit is still going to be that 7/3, the ratio of the leading coefficients. But now I need to check the sign. If I imagine plugging a negative in here, a negative squared is going to become positive. If I plug in a negative on top, it's still going to be negative. 7 times the negative would still be negative. And I'm doing this because I'm going to negative infinity. So a negative divided by positive is going to make the answer negative 7/3. Okay, so this was a big, long video of all kinds of examples of limits to infinity.